So last class we discussed about compound bars, how to find the stresses as well as forces in compound bars of same length or different lengths using the two conditions, equilibrium condition and strain compatibility condition. So today we will discuss about some important concepts like principle of superposition. So principle of superposition means let us take a bar like this, subjected to some forces like this. So this portion is one segment, this is another one, this is another one, made of same material but different length may be there. We have done problems on this type. I have taken four forces here: P1, P2, P3, P4. P1 and P1 is a tensile force C away from the bar. P2 is another tensile force away from the bar. P3 is acting like this. P4 is acting like this. So there are four forces I have taken here. They have some numerical values, 100 Newton, 200 Newton, like that. So the meaning of this is, suppose if you take the total force acting on this bar, algebraic sum you have to take, assuming forces acting towards right positive, towards left negative. So this P1 becomes minus. So sigma P is the total force acting on the bar, minus P1 minus P2 plus P3 plus P4. Okay, so that is the total force. Now, according to principle of superposition, whatever effect of the total force is there, or the net force, you can call it as net force also, on any body or structure. Here, that bar is the body. It will be equal to the sum of the effect of individual forces on the body. Okay, so what the meaning of that is, whatever effect of the sigma p is there on this bar, it will be equal to the effects of P1, P2, P3, P4. Some of the effects of P1, P2, P3, P4 on the bar. That is the meaning of principle of superposition. That means you are superposing the different forces on the same object, and you are finding the net effect of that those forces on the bar. So some of the forces may be tensile, some of the forces may be compressive. So the net effect you are going to get by adding the individual effects of all the forces. So effect may be, it may be stress, it may be strain, it may be deflection, it may be deformation, moment, anything. So they are all called the effects of force. Statement is like this: the total effect of the forces acting on a member is equal to the sum of the effects due to individual forces taken separately. That's what I told. So effect of P1 plus effect of P2 plus effect of P3 plus effect of P4 on this. Maybe let us take deformation, delta L. So delta L1, delta L2, delta L3, delta L4. If you add them, so it will give the effect of the total force acting on the ball. For example, this is 10, this is 20, this is 30, this is 40. Then what happens? Delta L due to 10 plus delta L due to 20 plus delta L due to 30 plus delta L due to 40. That will be equal to delta L due to delta P, sigma P. That is the name. So you have to find the effect of each force on the bar, and we have to add them. We have to add them. So then it will give the uh, total effect. The deformation due to sigma p is same as the sum of the deformation due to P1, P2, P3, and P4. Effect may be in the form of stress or strain or deflection or deformation or moment, anything. So bending moment we will discuss later. So, but there is some limitation on this principle of superposition. So, what are the limitation? This principle is applicable only if the strains and stresses developed are proportional to the forces causing them. So, the stresses and strains, whatever going to develop plastic state. So if they are in elastic limits, strains will be very small. So when these two conditions are satisfied, then only this principle of superposition can be applied. Otherwise, it cannot be applied. That is the meaning. Now, next, let us define the next elastic constant called modulus of rigidity or rigidity modulus. So you know about Young's modulus. or modulus of elasticity E, capital E, which is given by the ratio of linear stress to linear strain within elastic limits. That is the definition of Young's modulus E, and we have done some problems also on that. There is another constant called modulus of rigidity or rigidity modulus, which is denoted by G or C. In some books they denote it as C, some books they denote it as C. So, according to the definition of that is, it is to define that, first we have to define what is called as shear stress. Shear stress, which is denoted by tau. It's a Greek letter tau, which is used to denote the shear stress. So shear stress is definition is same as that of normal stress, but here F is the shear force. We call the force as shear force. See the difference between shear force and normal force. Normal force will be acting here. Normal force means tensile or compressive force is called as normal force. Normal force always acts normal to the area. Normal means perpendicular to the area like this. But whereas shear force acts parallel to the area. Parallel to the means or tangential to the area. So shear force, that is why it is also called as tangential force. So shear force, tangential force, both are same. So normal force will be normal to the cross sectional area. Now here F by A, F by A. So shear stress is given by this whatever shear force is acting divided by area. Area is this. This is the area, cross sectional area in Newton per millimeter square. Now what is the effect of this? Let us say effect of this will be this element or whatever bar I have taken, it will distort like this. See, if F is acting like this, parallel to that, elongation will take place of assuming that this bottom edge is fixed. Bottom edge is fixed. So here, the top edge, what happens? This point moves to this point. This point moves to this point, where the deformation is taken as delta. So this is delta. And if you take h as the thickness or the edge height, then and this gamma, this is the gamma is the angle. Gamma is called as the angular deformation. Delta is called as the linear deformation. There is a relation between these two. You know that tan gamma is equal to delta divided by h. Delta divided by h. Okay. So tan gamma will be taken as equal to gamma. Tan gamma will be equal to gamma. Okay. So here, this when gamma is very small, this gamma can be equated to tan gamma, which is given by delta by h. So that or you can take this as since tan gamma is equal to gamma, gamma can be written as delta by h. So this identity holds good when gamma is very small. Very small means it will be in terms of 0.01, 0.001 radian like this. So gamma should be in radians. So this identity you might have learned in mathematics already. So when theta is very small, sin theta can be equated to theta, tan theta can be equated to theta. That's what. And cos theta will be equal to 1 when theta is very small. That is the identity we are using here. So here this gamma, tan gamma is there, that can be equated to gamma. So when tan gamma is equal to gamma, so tan gamma we know that from this triangle it is delta divided by h. So gamma is equal to delta divided by h. So this gamma is called as the shear stress. So shear stress is F by A, force divided by area. So gamma, which is delta by h, is called as the shear strain. Now the ratio between these two, shear stress and shear strain, within elastic limits is known as the shear modulus or modulus of rigidity or rigidity modulus. So this is also called as, there are three words for this. So modulus of rigidity, rigidity modulus or shear modulus. All the three are same. So G is equal to tau by gamma. So this definition of G will be, it is the ratio of shear stress to shear strain. Shear stress is shear force divided by area or tangential force divided by area. It will act like this. Whereas normal force will act perpendicular to this. Shear force will act parallel to the area. So this area we have to take now. The top area we have to take. So that is the meaning. So modulus of elasticity, modulus of rigidity or shear modulus or rigidity modulus is given by tau by gamma. So tau is the shear stress, gamma is the shear strain, and its unit is Newton per mm square only, because tau is expressed in Newton per mm square. Gamma doesn't have any units. It is just a number. Okay. It is just a ratio. So tau by gamma is Newton per mm square. So it is the ratio of shear stress to shear strain within elastic limits. That is the definition of modulus of rigidity. So difference between modulus of rigidity and modulus of elasticity is modulus of elasticity is the ratio of linear stress to linear strain, okay, within elastic limits, whereas shear modulus is it is the ratio of shear stress to shear strain within elastic limits. So this is about modulus of rigidity and shear stress and shear strain. Next, one more important parameter or the elastic constant we have, that is Poisson's ratio. So Poisson's ratio normally it is denoted by mu or 1 by m. In some books they use it as 1 by m. Some books they use it as mu. So mu or 1 by m. So for defining Poisson's ratio, we need two strains. One is linear strain, another is lateral strain. So all of you know that when a bar is subjected to tension force like this. So here P is the tension force on this acting on the circular bar, let us say. L is the initial length. When it is subjected to tensile force like this, the bar gets elongated. It gets elongated, so length will increase. So L plus delta L is the length, new length. Okay, delta L is the increase in length. So when length increases, diameter reduces here. So because the volume should not change, mass of the bar should not change. When length increases, diameter reduces. So if you take the ratio of change in diameter to initial diameter, so initial diameter is d, a change in diameter is delta d. So here delta d, of course, it is a negative quantity because reduction in diameter. So that ratio is called as lateral strain or transfer strain. So two types of strains will be there. One is linear strain. Linear strain means along the length. Along the length of the bar, if it is subjected to tensile force, length will increase. It gives rise to linear strain or longitudinal strain. And along the diameter or in the other direction, lateral direction, we call it as lateral direction. This is longitudinal direction. The perpendicular to longitudinal is lateral direction. Diameter is the lateral direction. Along the diameter reduces. So it is the ratio of reduction in diameter divided by original diameter is called as lateral strain. It is also called as transverse strain or lateral strain. Okay. Now, if you take the ratio between these two, which acts at right angles to linear, Poisson's ratio is the ratio of lateral strain to linear strain within elastic fields. See, lateral strain is this delta d by d, linear strain is delta L by L. So if you take that ratio, epsilon lateral divided by epsilon linear, this is the definition of Poisson's ratio. So in the case of for the value of Poisson's ratio differs from material to material. So of course here for steel it varies from 0.25 to zero point 0.3. Concrete it varies, it is 0.15. Rubber it is 0.5. So it depends on the material type. Hmm? All these values, Young's modulus value, rigidity modulus value, Poisson's ratio value, it depends on the type of material of the bar for which the force is subjected. Now, another figure I have taken here. See, this is a circular bar. In the case of a circular rod, diameter becomes the lateral dimension. Whereas in the case of a rectangular bar, there will be two lateral dimensions. One is width, another is thickness or depth. You can call it as depth. So width and depth. This is length. L is the length. B is the width. D is the depth. If you take like that, so if I take x direction as length direction, y direction as depth direction, z direction as width direction, then you will be having two lateral strains here. So one linear strain is delta L by L, that is same, that is epsilon linear. But lateral you have two strains here. In the case of circular rod, what happens? Diameter will be there in both the directions. So this is also diameter, this is also diameter. Whereas in the case of rectangular bar, one will be breadth, another will be depth. So they may be equal or they may not be equal. If they are equal, it becomes a square bar. If they are not equal, then it is a rectangular bar. So that means you will be having two lateral strains here. One corresponds to the breadth, another corresponds to the depth. So these are the things I have written. Epsilon linear means it is in x direction. Epsilon lateral will be there in y direction as well as in the z direction. So z direction is this, y direction is this. I have shown in the cross section. So if you take epsilon lateral in y direction, Y direction is this depth direction, delta d by d, where d is the initial depth, delta d is the decrease in depth. So naturally it decreases in the other direction. In x direction it increases, length increases, but in y and z directions the length decreases. That is, the breadth and depth decreases due to tension force. Now in the z direction is along the width direction. Along the width direction, if you write on the same lines, change in width divided by initial width. So that is the lateral strain in the z direction. That means what I wanted to say is, in the case of circular bars, x direction is length, y and z both are equal to diameter. So this is y, this is z. So both are equal to diameter. Whereas in the case of rectangular bar, x direction is length direction, and I have taken depth direction as y direction and width as z direction. Then this is the expression for a lateral strain. So linear strain and lateral strain. So if you take the ratio of lateral strain to linear strain within elastic limits, that is called as Poisson's ratio. Third elastic constant. These are called as elastic constants. First elastic constant is Young's modulus E, that is linear stress divided by linear strain. Second one is modulus of rigidity or shear modulus. It is the ratio of shear stress to shear strain. All are within elastic limits. Third one is Poisson's ratio, ratio of linear strain to lateral strain to linear strain within elastic limits. The fourth one is bulk modulus. So fourth elastic constant is the bulk modulus of elasticity denoted by K. So how to define bulk? Bulk means volume. Bulk means volume. So when you take a three-dimensional element like this, sigma x is the stress in this direction, x direction. Sigma y, let us take this as y direction. Sigma y is the stress in y direction. Sigma z is the stress in z direction. Okay. Sigma z is like this. All I have taken tensile. See, I have taken all away from the element. That means all are tensile stresses. Sigma x, sigma y, sigma z. All the three are tensile stresses in the respective directions. They are mutually perpendicular to each other. So they are the normal stresses. Sigma x, sigma y, sigma z, they are called as the normal stresses. If sigma x, sigma y, sigma z are all equal, then they are called as bulk stress. So if sigma x is equal to sigma y is equal to sigma z is equal to sigma, let us say it is equal to sigma, then it is called as bulk stress. If all the three are equal, or you can call it as sigma k also. So what happens? What is the effect of that? So once when this bar, when this element, three-dimensional element is subjected to stresses in all the three directions, the effect is it tries to elongate in all the three directions. See, it elongates in this direction, it elongates in this direction, it elongates in this, because it is tensile force. Tensile force is applied, tensile stress will develop. So these tensile stresses will develop only when tensile force is applied in all these three directions. Then what is the effect of that? If V is the initial volume, delta V is the change in volume. So we have to take care of volume now. It is not only length. So it expands in all the three directions. Along the length it expands, along the width it expands, along the depth also it expands. So that's why we have to take the change in volume. Now if you take the ratio of change in volume to initial volume, that is called as the volumetric strain. So see, in strains we have different types: linear strain, lateral strain. Now this is volumetric strain. Volumetric strain is nothing but the ratio of change in volume to initial volume within elastic limits. Now bulk modulus is defined as the ratio of bulk stress to volumetric strain within elastic limits. It is also expressed in Newton per mm square. That is sigma k divided by epsilon v. So in the denominator, strain is volumetric strain here. Numerator, it is bulk stress. What is bulk stress? When the stress in all the directions are equal, then we say that it has the bulk stress. So there will be change in volume in that case. So the its unit is also Newton per mm square, because sigma k is expressed in Newton per mm square. Epsilon v does not have any unit. Change in volume will be in millimeter cube. Initial volume also will be in millimeter cube. So there is no unit for volumetric strain. Okay. So that means among the four elastic constants, first one is Young's modulus. Unit is Newton per mm square. Ratio of linear stress to linear strain within elastic limits. Young's modulus value E, capital E. Second one is modulus of rigidity or shear modulus, denoted by G or C. It is the ratio of shear stress to shear strain within the elastic limits. So unit is Newton per mm square only. Next, third one is Poisson's ratio. It is the ratio of lateral strain to linear strain within elastic limits. So its unit is, it has no units, unitless, because it's the ratio of strain divided by strain. Strain does not have any unit. So totally mu or 1 by m also does not have any unit. I have given some values of Poisson's ratio for some of the materials here. Then the fourth one is bulk modulus of elasticity. It is the ratio of bulk stress to volumetric strain within elastic limits. Once again, its unit is Newton per mm square. So these four constants, E, G, K, mu. So E Young's modulus is E, bulk rigidity modulus is G, bulk modulus is K, Poisson's ratio is mu. They are called as elastic constants. So this is about elastic constants. Later on, we have to derive the relationship between these four elastic constants. So define elastic constants, derive the relationship between them. So like then you can ask. There are two important derivations that I will take up later. So this is in Newton per mm square. This is in Newton per mm square. This is in Newton per mm square. This no unit. So this is about the modulus of rigidity, principle of superposition, and its limitations, modulus of rigidity, Poisson's ratio, and bulk modulus of elasticity. Now we will come to the very important law called generalized Hooke's law. So you know about Hooke's law. I have told you in the earlier classes about Hooke's law. Hooke's law states that stress is directly proportional to strain within elastic limits. That is Hooke's law. Sigma is directly proportional to epsilon, or sigma is equal to E into epsilon. So where E is Young's modulus. So that is a linear variation of stress with respect to strain. That is, if you take the slope of that stress strain graph in the linear region, you are going to get that Young's modulus value that I explained earlier. Now there is one thing called generalized Hooke's law. So that Hooke's law is defined only if the stress is unidirectional. Unidirectional means only tensile force is applied in only one direction, or compressive stress is applied only in one direction. That is called as unidirectional. Whereas generalized Hooke's law is valid when the stresses are developing in all the three directions, x, y, z. In a three-dimensional element, sigma x is the, see here, uh, let us assume that this element, three-dimensional element or block, rectangular block, is subjected to tensile force in all the three directions. X direction, this is y direction, this is z direction. So x is this, y is this, z is this. So there will be two faces for each direction. So you can see that here sigma x is acting like this. In the opposite face, it will act like this. Sigma x will act like this. So sigma x will be acting, is acting over this face. Please note, this is the area we have to consider for for finding the sigma x, and this is the area, opposite face area you have to take for this sigma x. Then sigma y is acting over this area. The normal to this area, sigma y will be acting top and bottom, top face and bottom face. So this area we have to take for this sigma y. Then sigma z front and back. So left and right faces sigma x, top and bottom faces sigma y, front and back faces sigma z. So this is sigma z, this is also sigma z. Corresponding strains are epsilon x, epsilon y, epsilon z. See sigma x, sigma y, sigma z, they are the stresses. Epsilon 6, epsilon y, epsilon z, they are the normal strains. These are normal stresses. They are normal strains. Now there is a relation between how to find these strains in such a case. If you know the values of stresses, how to find the value of strain in all the three directions. So in this case, what happens? I have taken sigma x, sigma y, sigma z as normal stresses along x, y, z directions respectively. Epsilon x, epsilon y, epsilon z, they are the normal strains. So normal strains in that direction. Now what happens, since here the stresses are acting on all the three faces, you have to consider the strains. For example, epsilon x. Epsilon x is the strain in x direction. This strain will be due to sigma x, sigma y, sigma z, all the three stresses. See, this is very important here. Whereas if only one stress is acting, unidirectional stress, see epsilon is calculated only by using sigma divided by E, that formula. Sigma divided by E is used to to calculate strain if the stress is only acting only in one direction. But here the stresses are acting in all the three directions. In such a case, this epsilon x is obtained by principle of superposition using the effect of the sigma x, sigma y, sigma z in this direction. We have to understand this very clearly. The epsilon x is obtained by taking the effect of sigma x, sigma y, sigma z, all the three. Similarly, epsilon y is obtained by taking the effect of all the three stresses, sigma x, sigma y, and sigma z. Epsilon z is also obtained by taking the effect of all the three stresses. So here, that is why this is called as generalized Hooke's law. So it states that generalized Hooke's law states that the strains in three mutually perpendicular directions of a body subjected to stresses can be found out by using Hooke's law and principle of superposition. Hooke's law means if you take sigma x here, epsilon x is related to sigma x. How it is related? Epsilon x is equal to sigma x divided by E. That we have seen earlier. So by knowing the stress, we can find out strain in that direction just by dividing the stress value by Young's modulus. So sigma x by E gives the value of epsilon x in this direction. Now, suppose, but that is Hooke's law. If you are applying principle of superposition also, then sigma y also has got effect on this epsilon x. Because it's a compact three-dimensional element, sigma y also has got effect on epsilon x. Sigma z also has got effect on epsilon x. Now, how to find that? That is important. Now, considering epsilon x, epsilon z are the strains in x and x, y, z directions due to sigma x, sigma y, sigma z. Now, what I will take epsilon x as Ex. I take it as Ex. Epsilon x, epsilon y, epsilon z, they are the strains in x and y directions only due to sigma x, sigma y, sigma z. Now I will use one more notation called Ex. What is this Ex? Ex is the strain in x direction due to all the three stresses. See, Ex is different, epsilon x is different. Epsilon x is only due to sigma x. Epsilon y is only due to sigma y. Epsilon z is only due to sigma z. Whereas Ex is the strain due to all the three. So we have to combine the effect of all the three stresses. That is the meaning of principle of superposition. Now the meaning of that is Ex is equal. Now let us find out the strain in this direction. Ex is the total strain in the x direction due to all the three stresses. So Ex will be strain due to sigma x plus strain due to sigma y plus strain due to sigma z. All the three we have to add. Now what is the strain due to sigma x? Strain due to sigma x is nothing but sigma x by E. Sigma x by E. This we know. So because within elastic limit stress is directly proportional to strain. So in x direction due to sigma x, strain is sigma x by E. But coming to sigma y, now you should be very careful here. Now we are finding strain in x direction due to sigma y now, not due to sigma x. Due to sigma x, it is sigma x by E. Due to sigma y, how to calculate? So for that, I have written here. You see here, epsilon x is sigma x by E in x direction. Epsilon y is sigma y by E in y direction. Epsilon z is sigma z by E in z direction. Now you know, according to the definition of Poisson's ratio, mu is equal to epsilon lateral divided by epsilon linear, or epsilon lateral is equal to mu times epsilon linear. That means here we have to take a term called lateral strain. So this is the lateral strain term. So what is lateral strain? Mu into linear strain. As per the definition of Poisson's ratio, so lateral strain is given by mu into linear strain. So mu into linear strain. What is the linear strain in that direction? In the y direction, due to sigma y. Due to sigma y, what is the linear strain in this direction? That is nothing but sigma y by E we have to take. So due to this stress, it is sigma y by E. Only thing is it should be multiplied by mu. And another thing is I have written minus here. Why it is minus? What happens when when tensile stress is there in this direction? In x direction, it becomes compressive stress because the volume if it elongates in this direction, it should contract in this direction. Contraction means I have to take strain negative. So that is why minus has come. So in the direction, in sigma x direction, it is positive. In y direction, z direction, it will be negative. Because negative means I have taken tensile as positive. So all the three I have taken tensile. Sigma x, sigma y, sigma z, all the three stresses I have taken it as tensile for explanation. In that case, what happens? Sigma x, due to this, it is positive. Sigma x by E is the strain due to sigma x in this direction. But see, due to the sigma y in this direction, it is negative because positive in this direction, automatically lateral strain becomes negative. I explained that by taking that circular rod and rectangular rod, when length increases, diameter reduces. When length increases, breadth and width reduces. That concept we have to use here. So that is, I have taken negative here. So this step is very, very important. Similarly, in z direction also, mu times sigma z by E. So sigma z by E is the linear strain that should be multiplied by Young's modulus to get the lateral strain. So please note that the first one is the linear strain, second and third terms are lateral strains. If you add all these three, you are going to get the total strain in x direction. So we have used so the sigma x by E, sigma y by E, sigma z by E. These terms, that is nothing but Hooke's law. And principle of superposition means this is positive, this is negative, this is negative. So if you write it by taking 1 by E common, 1 by E you can take outside here. If you take 1 by E common, it becomes sigma x minus mu you can take common from these two, mu into sigma y plus sigma z. Like that you can write. On similar lines, if you want the strain in y direction, due to all the three. So due to all the three, here Ey means similar, just like Ex. So what is Ex here? Strain in x direction due to all the three stresses. Then what is Ey? Similar lines, if you define, Ey is nothing but strain in y direction due to all these three stresses, sigma x, sigma y, and sigma z. In that case, what happens? Just see how we can write. So in that case also, strain due to sigma x plus strain due to sigma y plus strain due to sigma z will come. In that case, in the y direction, sigma y by E will come first. Okay, sigma y by E instead of x, y will come. Sigma y by E will come. In x direction, it is minus mu times sigma x by E. In z direction, it is minus mu times sigma z by E. That means the difference between these two is x is replaced by y here, and the remaining here this becomes x. This remains as it is. Similarly, Ez, what is Ez? Ez is the strain, total strain in Z direction due to all the three stresses. So in that case, what happens is X is replaced by Z, and here Z is replaced by X. So this Y remains as it is. So in that case, this is the expression. That means if you know how to write the total strain expression in the case of three-dimensional stress system, this is called as three-dimensional stress system because stresses are there in all the three directions, x, y, z. So sigma x, sigma y, sigma z, they are the stresses in the three mutually perpendicular directions, x, y, z. We are finding strains in all the three directions, x, y, z directions, due to all the three stresses. That is why it is called as generalized Hooke's law. If you are finding strain in only one direction due to only one stress, that is Hooke's law. Okay, this is generalized Hooke's law, means we are using that concept along with principle of superposition to find the strain in all the three directions by adding the effects of linear strain and lateral strain. So in this, the first term is linear. If you are finding Ex, strain due to sigma x is linear strain due to sigma y is lateral strain due to sigma z is also lateral strain. Okay, whenever that lateral strain term comes into picture in the other two directions, mu will come into picture. And if the force is tensile, if the stress is tensile in that direction, then we have to take the opposite sign. That is because due to tensile stress, that material elongates in that direction. In the other two directions, it contracts. So that's why we had to take negative sign there. Suppose in the instead of taking tensile, they may give compressive. If they give compressive, it will be negative in that direction because the length will reduce, and positive in the other two directions. In the other two directions, the material elongates. So please keep that in mind. If they give tensile stress or tensile force, material elongates in that direction, and in the other two directions, it compresses. That means that length will reduce, width or depth, whatever it is, that will dimension will reduce. If the material is subjected to compressive stress or compressive force in one of the directions, it is negative in that direction and positive in the other two directions. So like that we have to take. So if you apply that concept, this is how we are going to get the generalized hooks. Now I have taken two more examples here. Please understand here. See, here I have taken sigma x compressive. See here. Sigma x is compressive, sigma y tensile, sigma z compressive. So sigma z is compressive, sigma x is compressive, sigma y is tensile. So I have written here tensile, compressive, compressive. Towards the block, if you take the arrow, it is compressive. Away from the block, if you take the arrow, it is tensile. Now, if I want to apply generalized hooks for this, let us say this is x direction, y direction, z direction. So Ex is the strain due to all the three, epsilon x, sigma x, sigma y, sigma z. Now, first I will write due to sigma x. Sigma x is compressive here, so I have to take minus sigma x by E, minus sigma x by E. See here. Whereas if you go for sigma y, if you go to sigma y is tensile. See, sigma y is given as tensile. So in this direction it is tensile. So in the other two directions it becomes compressive. That means I had to take minus only in this direction. Even though this is tensile here, in this direction it becomes minus. So minus sigma y by E into mu. Okay. Next, coming to sigma z. Sigma z is compressive in this direction. See, observe here. Compressive in z direction. If it is compressive in z direction, it will be tensile in x and y directions. So contraction will be there in this direction. Elongation takes place in the other two directions. That is why I have taken positive. So due to sigma z, the effect of sigma z is positive in x direction. It is negative in z direction, positive in x direction, positive in y direction. So sigma z by E into mu. So this is the total strain. You can take 1 by E common and you can write, you can simplify the expression. Suppose if you want Ey, let us say Ey. What is Ey? Ey is the strain in y direction due to all three stresses, sigma x, sigma y, and sigma z. So let me take first sigma y. So in that direction only, sigma y is tensile. Tensile means positive. In that direction I am writing, So Ey means strain in y direction. In that direction only sigma y is tensile, therefore it is positive. Okay. Then coming to sigma x. Sigma x is compressive in x direction, therefore it should be tensile in y direction. See, understand here. I am writing in y direction, So tensile in y direction means I have to take plus mu times sigma x by E. I have to take. Next, due to this sigma z is negative in z direction. Therefore, it is positive in y and x direction. I am writing the strain in y direction, so I have to take plus. So plus mu times sigma z divided by E. So that is the expression for Ey. Similarly, if you take the expression for Ez is the total strain in z direction due to all the three stresses, sigma x, sigma y, sigma z. In that case, first I will take this sigma z. Sigma z is compressive. Since it is compressive, I have to take a negative. So minus sigma z by E. So that's what I have written here. Minus sigma z by E is the strain in this direction due to sigma z. Since it is compressive negative in this z direction, its effect should be positive in the other two directions. So in x direction, its effect is positive. That means in this direction, since this is compressive, so in the x direction, what happens? It is positive. That is plus mu times sigma x by E. We have to take. So I have written here. Next, in the other direction, in y direction, this is tensile in this direction. but it will be compressive in this direction. Therefore, it is minus sigma y by E. So this is what I wanted to tell. So one more example I have written here. You can just go through that and you can find out how it has been written. So total strain is given by the sum total of the strains in all three directions. One is linear strain, the other two terms of lateral strains. So you have to be careful there. The first term is the linear strain, second and third terms are lateral strains. So if tensile stress is there in one direction, naturally it will develop compressive stress in the other two directions, which are mutually perpendicular direction. That's why we have to take compressive stress as negative, tensile stress as positive, use the sign convention. This is how you are going to get the total strain. So you have to understand this generalized Hooke's law clearly. It is a combination of Hooke's law and principle of superposition. So why principle of superposition? Because we are taking three-dimensional stress system here, sigma x, sigma y, sigma z. They are the three-dimensional stress systems. We are finding the strain in one direction due to the effect of all the three stresses, sigma x, sigma y, sigma z. So linear and lateral strains both will come into picture here. So this is about generalized Hooke's law. Now we will see how it can be used for finding the volumetric strain in rectangular bar. So here you see volumetric strain in a rectangular bar, very simple definition. So this is generalized Hooke's law. If they ask you to explain, state and explain generalized Hooke's law, we have to write the statement which I have written here, plus the sketch, then equations. All these expressions you have to write, state and explain generalized Hooke's law. Now let us see how we can find out the volumetric strain in a rectangular bar. Rectangular bar. So I will consider a rectangular bar of dimensions x, y, z like this. See, x is the length, y is the width, z is the depth or thickness. So corresponding stresses, I will take sigma x like this, sigma y like this, sigma z like this. All the three I have taken tensile stress just for the derivation purpose. When the bar is subjected to tensile stress in all the three directions, volume will increase. There will be increase in length in all the three directions, so which gives rise to increase in volume. So volume will get increased. Suppose if it is subjected to compressive stress, then volume gets reduced. The initial volume here is x into y into z, that you know. Volume of a rectangular bar is x into y into z, length into width into height. So final volume, I will take it as V plus delta V. So here delta V is the change in volume, which is more than the initial volume because tensile stress is developed. So delta V by V is nothing but your volumetric strain. So volumetric strain is defined as change in volume to initial volume. So initial volume is this, final volume is this. Change in volume is difference between these two. So what happens here when this rectangular bar is elongated in all the three directions? Initial length x becomes x plus delta x, y becomes y plus delta y, z becomes z plus delta z. So this is your final volume. So in all the three directions, elongations will be there due to the stresses. So now if you simplify this, change in volume is delta v. Delta v means this minus this. So the product of these three minus xyz gives the change in volume. If you simplify, if you multiply each and every term here and subtract this, neglecting the smaller quantities. For example, here what happens, delta x, delta y, delta z are the deformations along xyz directions which are very small. So you know that delta x, delta y, delta z, they are all very small. When they are all very small quantities, their products also will be very small and can be neglected. For example, in this, you can neglect this term. Which one? This delta x into delta y term you can neglect. Wherever you have two or three delta terms, product of two or three delta terms, that can be neglected because it becomes very, very small. And this also you can neglect. Delta y into delta z you can neglect. Delta x into delta y into y, this term you can neglect. This also you can neglect. Delta x into delta y into delta z, you can neglect this also. So by neglecting these four terms, 1, 2, 3, 4 terms, and you, by cancelling this xyz term, so you'll be left with so very simple. So delta v is equal to change in volume is equal to this only three terms you'll be left with. If you want EV is nothing but your volumetric strain. So volumetric strain EV is equal to delta V by V according to the definition. So delta V is now this after simplification. Divided by V is XYZ, initial volume. If you take the term separate and if you simplify, so you'll be getting like this EV. So EV is the volumetric strain is equal to delta X by X plus delta Y by Y plus delta Z by Z. So what is the delta X by X? Delta X by X is nothing but your epsilon X. Epsilon X, this is epsilon Y, this is epsilon Z. So we can write it as, so epsilon X plus epsilon Y plus epsilon R, I have written here EX plus EY plus EZ, you can write like this also. So volumetric strain in a rectangular bar is the sum of the linear strains in three directions. So you can write it as epsilon only. You don't confuse. Instead of EX, you please make it as epsilon X. So epsilon X plus epsilon Y plus epsilon Z will give the total volumetric strain of the rectangular bar. So how to find this Ex, Ey, Ez? That is using the uh, generalized Hooke's law. You take it as Ex, Ey, Ez only because this delta X by X consists of the effect due to all the three stresses. Okay, due to all these three stresses, sigma X, sigma Y, sigma Z. So that is why I have written Ex, Ey, Ez only. You write it like this only. So the problems will be given like this. Once the stresses are known, you can find out these strains in all the three directions using generalized Hooke's law. Then add them. You are going to get the volumetric strain. So that's what I have written here. Ex, Ey, Ez are found using generalized Hooke's law. They may be positive or negative. So depending on the that plus minus sign and all. So it can be positive or negative. Then find EV. EV means sum of all these three. So if you get negative, just take it as negative. So for example, Ex may be 0.01, Ey may be minus 0.02, Ez may be plus 0.03 like that. Then you have to add all the three algebraically. Then you can find out the change in volume by using this formula. We know that EV is equal to delta V by V. V is known, initial volume we will be knowing. EV is found out using this. Take the product of that, you will get delta V. If delta V is positive, then expansion. So that means volume will increase. If there is an increase in volume, if delta V is negative, then it's a contraction in the volume. That is the meaning. There is a decrease in volume. That is the meaning. So problems we have to do on this finding volumetric strain or change in volume, all those things that I will discuss in the next class. So today I had explained you about, just I will brush up. Yes, recall I explained about the principle of superposition. That means the effect of net effect of number of forces or resultant force you can call on a structure or on a bar like this. In sense of it is we take some compound bars like this is the same as the sum of the effects due to individual forces acting on that bar. That is principle of superposition. It has got two limitations which I have told. Then I defined about modulus of rigidity or shear modulus, ratio of shear stress to shear strain within elastic limits. Unit is Newton per mm square only. Then Poisson's ratio, ratio of lateral strain to linear strain, no units for that within elastic limits. Then bulk modulus of elasticity K is the ratio of bulk stress to volumetric strain. Unit is Newton per mm square. Then I explained about generalized Hooke's law, which takes into account the combination of both Hooke's law as well as principle of superposition, from which you can find out the strains in all the directions due to the effect of the stresses developed in all the three directions. That is obtained from generalized Hooke's law. When you are using generalized Hooke's law, tensile strain is taken as positive, compressive strain is taken as negative. So that is sign convention you should follow. Then I explained about how to find the volumetric strain in a rectangular bar. So volumetric strain is given by change in volume to initial volume. So initial volume is XYZ, change in volume will be delta V. So final volume is V plus delta V, that is each dimension will increase. So you'll be having X plus delta X, Y plus delta Y, Z plus delta Z, all those things. Then take the difference, neglect the small product of small delta terms, and finally you will be getting delta V only carrying three terms like this. Then divide the delta V by the initial volume, you will get the volumetric strain. So volumetric strain is given by the sum of the strains in all the three mutually perpendicular directions. Algebraic sum is not only sum, we call that algebraic sum. So some of them may be positive, some of them may be negative. Take the algebraic sum of the strains in all the three directions, you will get the volumetric strain. After getting volumetric strain, you can always find the change in volume due to the given force system. So we will take up problems on this later. Okay. So this is what I wanted to explain today. You have to thoroughly sit and write all this. Otherwise, you will be getting a lot of doubts. So you have to understand the generalized hooks, the very important concept in solving problems. So I think I will stop here. So tomorrow I will continue with the other concepts. If you have any doubt, you can ask me. I will just take the attendance. Nineteen 005.
Present, sir.
007.
Present, sir.
011. 011.
Present, sir.
13.
Present, sir.
14. 14. 15.
Present, sir.
17.
Present, sir.
18.
Present, sir.
19.
Present, sir.
That's all. 2, 3, 4, 5, 6, 7. 14 is not there. Left off, 14. I'll put absent. So all of you should understand what I have explained today. Tomorrow I will take up the remaining things. This is a very big chapter. First chapter is a very big chapter. You should be thorough with that. Okay. Whatever problems I had explained in the classes, you had to practice. Okay, I will stop the class.